Mr. Jameson has 180 feet of fencing that he wishes to use to create a rectangular corral for his horses. He also wants to use some of the fencing to divide the rectangular corral into two smaller corrals so that he can separate his horses at feeding time. What's the largest corral he can create using all 180 feet of fencing? So as always, you want to begin with a diagram. So we're looking at creating a large rectangular corral, but then he also wants to use fencing down the middle somewhere to divide the corral into two smaller corrals. So our diagram would look something like this. But we also want to label our diagram. So you have to think about what you don't know about this problem. So what do I not know about the rectangle? And of course, I don't know my dimensions. I don't know the length and I don't know the width. So I'm going to go ahead and use L for length and I'll use W for width. So now I've got a labeled diagram. So our next step is to focus on the goal in the problem. What are we trying to maximize or minimize? And on this one you can see we want the largest corral possible. So that means we want to maximize the area of this large rectangle. So we want to maximize area. And I recommend that you actually write down your goal, because whatever it is that you're trying to maximize or minimize, that's what you want to begin with. And you want to write an equation for that. So if we're maximizing profit, start with a profit equation. If we're minimizing area, start with an area equation, or whatever the case may be. Since we're maximizing area, we'll start with an area equation, and we want the area of this entire rectangle, which would be length times width. Now the problem with this equation is that we have too many variables. This would be an equation in two variables. We have two inputs, length and width, and then our output of area. So we want to eliminate a variable. And usually we have some sort of a constraint that we're working with. So we want to write what I call a constraint equation, or it's a second equation that involves the variables in the problem. So when you reread the problem, you'll notice that we have not used the fact that he's limited to 180 feet of fencing. Now think about where this fencing actually is going to go. The fencing is going to go along the outside to create the larger corral. That would be the perimeter of this rectangle. But the fencing is also going to go down the middle somewhere to divide it into two smaller pens. So now let's update our diagram. We know that if the right-hand side has a width W, the left-hand side will also have a width W. But then the fencing that's going down the middle would also have a length of W as well. And then the opposite side of the corral we could also label as L. So now, if you think about your constraint equation, where the fencing actually has to go, it goes all around the four sides, but also down the middle. So that would be 2L plus 3W. And he wants to use all 180 feet of fencing, so that would be equal to 180. So that's our second equation, our constraint equation. Now we want to use this equation to substitute into our area equation and then eliminate a variable. And it is up to you which variable you solve for here in the constraint equation. You could solve for L, or you could solve for W. It's not going to make a bit of difference. So I'm going to go ahead and just solve for W. I'll take 3W here, subtract my 2L, so 180 minus 2L, and then divide by 3. So W will equal 60 minus 2/3 L. Then I always like to go ahead and put a box around my constraint equation, because this is my equation that relates length and width in case I need it later. But now I'm just going to take this equation and I'm going to substitute into my area equation. So area is equal to length times width, but now I have a new equation representing my width, 60 minus 2/3 L. Which now if you distribute this, we see we have 60L minus 2/3 L squared. And this is my area model. This is what I would call my model. It's also my function. If you didn't want to use just A, you could actually write it as A of L if you wanted to use function notation, because it's the area depending on the length. Now we want to move on to the maximizing portion of the problem. We want to figure out the maximum area possible. So we need to think graphically for just a second. And hopefully we can do this without our graphing calculator. We're inputting an L, we're outputting an A. And the shape of my graph is going to be a parabola, and it's downward facing because we have this negative. In fact, if you want to rewrite this, you may. This would be negative 2/3 L squared plus 60L. And perhaps that would help you see the negative leading coefficient a little more clearly. And then the y-intercept is going to be 0. Think of it as substituting in 0 for length. You're going to get 0 for your output. So we're going to have a parabola that looks something like this, downward facing with a y-intercept of 0. So then we see that the maximum is going to occur here, and that's going to be at the vertex. So just a reminder about the actual value in this case. When we compute the vertex, normally we think of it as x, y. But in this problem, the way our function is labeled and our diagram is labeled, we're going to be putting in a length and we'll be outputting an area. So L, comma, A will be the result. So easiest way to find our vertex here would be to go ahead and utilize our negative b over 2a formula for finding the vertex. Our b value is 60, so that would be negative 60, divided by 2 times a, which is negative 2/3. So we'll end up here with negative 60 divided by negative 4/3, which of course, yes, you can use your calculator for. I'll go ahead and do this by hand. So we're going to change our division into multiplying by the reciprocal. So that would be negative 60 times negative 3/4, which is going to give us a positive 45. So this is, remember, a length value. This is the length. This was corresponding to L. And this is the length that's going to yield the maximum area. So if you think about the actual vertex of the parabola, what we just found essentially the x value of the vertex. But you do need to go back to the problem to make sure that we answer it correctly. Make sure this is actually what the problem is asking us for. So if you go back to the problem, it says, what is the largest corral that he can create using 180 feet of fencing? So to me, this implies that we don't want just the maximum area, but rather we want the dimensions. So we have the length of 45, and looking on this page, you'll see we have two different equations. We have this area equation here that relates area and length, and we had our constraint equation here that related the width and the length. So if I want the dimensions of the corral, the dimensions of my corral would be the width and the length. Therefore, when I'm going back to substitute here and figure out where do I want to substitute in the length, I would want to substitute it here into my constraint equation in order to get the corresponding width, which would be the other dimension of the rectangle. So W equals 60 minus 2/3 L. We're going to use that. So I'll come back over here to our work. So we knew that W was equal to 60 minus 2/3 L. So if we substitute, then we can take 60 minus 2/3 times my length value of 45, and this will give us our width, which is 30. So it looks like when we have a width of 30 and a length of 45, that's going to yield the rectangle that has the largest area. And then if you want the actual area, the area would be the y value of our vertex. So once again, you would then need to come back to your area equation, which I've got written up here. There you are. My area equation, 60L minus 2/3 L squared. So if you want to, get rid of this here, you can go ahead and then also take the length and you can substitute it here into our area function. Our area function, so that would be A of 45. And that's going to give you the largest area, the actual area of the corral, which looks to be 1,350. But as always, please check those computations on your own calculator to make sure you're not making any sort of calculator error. So lastly, let's answer the question and include units. So we have a length of 45. That's going to be 45 feet of fencing. A width of 30. That's also 30 feet of fencing. And then the maximum area that we can create here is 1,350, and the units for that would be feet squared, or square feet, since that's an area measurement. So the dimensions, the overall dimensions would be a 30-foot by 45-foot rectangle, which will yield a maximum area of 1,350 square feet.